Need to find the settings. There we go. Okay, please screen share when ready.
Alrighty. So before I begin, I just wanted to mention, I think for the last session, I didn't get. I see the screen recording link for session 5, but it doesn't show specifically the recording for the link. So
Yeah. I could be behind. Sorry about that. I could be behind in uploading that, so it's just not available yet. But hopefully, you were able to, look at the homework and make progress on it even without the recording. But it will be there as soon as I get back to a reliable internet connection.
Alrighty. So then here is my screen. So I have two programs available, one for just modeling the plane dilemma, which now I realize is inaccurate, mostly because I have only one flight location. But I also have this plane. I also have the general solver for it. So first, I want to begin with just generally explaining how we could reduce a problem to Cubo, or at least let's say we have like pretty much what you suggested. We have these planes that are going to try and fly, right? We only have one plane, and we want to minimize the number of flights to a certain value m, right?
Well, we want to minimize conflicts.
Yes.
Yes. So sorry. Go ahead.
So in that case, for my analysis, in this case, we generally have two cases, right? We say we have a flight, right, of x sub 0, right? We can have flight. And we're going to have the constraint variable that x sub 0 equals 1, aka the flight is scheduled, right?
Yes.
So there are two conditions which we have to evaluate in that case, which I believe would be based on the idea that we would only have one plane. The first one is that we have to make sure that that the flight times do not conflict with one another. So for example, if I have a flight from, I'm going to annotate here, say I have a flight from, let's say I have a flight from 1 p.m. to 3 p.m. And then I have another flight from 1:30 p.m. to 3:30 p.m., then those flights will generally conflict. However, there is also the additional condition of where the plane is located, and currently my code unfortunately does not do that, so I will hope to update the code at least and make sure that is all sorted out so that it also includes flight location. But in this condition, for our flight location, we also have to consider where it is. In this case, I have currently 15 places, each with the capital of the most populated states in order. Like, for example, California is the most populated, then Texas, then Florida, and so on. So in that case, we also have to consider where the plane is at in each location. Like, for example, say that we have a flight. Let's say we decide to go from a flight. We begin with our plane in, say, Tallahassee, Florida, right? And we move to Sacramento, California, right? That's going to be our x sub 0. Now, let's say there's another flight that does have a condition of, instead of 1 p.m. to 3 p.m., it's going to be 3:30 p.m. to 5:30 p.m., right? But the problem is that flight goes from Austin, Texas to Albany, New York. Then unfortunately, I cannot book that flight because the plane is not at that location. So in this case, even though we have that plane pretty much at that location, which is very similar to it, so in that case, I've set up my problem in the way that's very similar to the traveling salesman issue. It's not exactly the same due to the traveling salesman problem requiring you to find the minimum amount of distance to travel between cities, while this problem just requires that you have the least amount of conflicts. But it's somewhat modeled in a similar way. But the most important part is that we can reduce this to Cubo based on the x sub I and x sub j. So I will go ahead and write this out. So in this case, we're going to have the formula. This is going to be the sum of I to j, of I to j, that exists for all n. I'm going to draw this out very carefully. For n. I apologize for the drawing, but in that case, we
Okay.
can have,
That's great.
then we have C of I and j. We then multiply that by x of I. And x sub j. And we're going to set this to a minimum amount as well. If we want to make the problem simple, we can also simplify it to be less than a certain value m. So in that case, we can have less than a certain number of constants. I apologize for the m. But we can just try and figure out through a certain algorithm whether or not we can find the least amount of conflicts given a certain value. So from here, we can also say that for x of I and x of j, we can leave this alone if that one constraint variable is 1. But if it is 0, then we want to avoid evaluating it in terms of computation time. So we could probably also include the, I believe what it was, a penalty. So it was something like p of x sub I or x sub j. I think x sub I, I'll do an I slash j to indicate that it's either I or j. So p of x of I or j minus 1 squared. If this evaluates to 0, then if this evaluates to 0, then we don't deduct any penalty. But if this is 1 or negative 1, which would evaluate to 1, then in that case, we induct some sort of penalty. I'm probably putting it in complicated terms, but I think in general, we don't really need this part of it. So I'll ignore it in further analysis. But in this case, we can just have this in general. Now, in this part, C of I of j represents if of two flights are conflicting, aka if and that represents the condition, and this represents the two conditions I talked about earlier, that number 1, those flights are not at the same time. Number 2, I can get from one flight to another has the same location. So for example, both flights have Sacramento, California as either a beginning or an end, not both, but not both in particular, because then you can't really create formulation because you can't create a condition where the two flights or okay. But yeah, in general, it's important that the two flight locations occur either at the start or the end, but they can't occur for I think I'm not explaining it well. I'm so sorry.
That's okay. Can we pause here, because I think there are multiple things going on. And first of all, thanks for taking the initiative, because even without the recording, you're able to flesh out, 90% of what we talked about in code and come up with this random sample data set, which is great, because that's how best to understand. That's how I understand these abstract problems, is to pick actual concrete data sets. So that's great. And the problems you described is, I would say it's 90% in agreement with what I was thinking, but it's not a Hamiltonian circuit or a realistic airline scheduling problem, because we're not requiring planes actually to be consistent. Like the way I phrased it to you is only the times needed to be compatible, like not conflict. But you're right. I mean, if a plane is ending in Sacramento, it can't pick up the next flight from Austin, even if it's 30 minutes, afterwards of free time, of slack time. So it's not realistic in that sense. So it's loosely an airline scheduling problem without this realistic constraint of requiring planes to connect and be in physically contiguous locations. And the M is the number of conflicts, which is roughly, at least a lower bound on the number of planes we need. We probably need more, especially if we wanted them to begin and planes to begin and end in the same spot between flights. So that's one thing. And don't worry about the contiguous locations, because that's a different problem. That's harder, and I don't know if it can be mapped to Cubo. That's more like a network flow graph problem, which is also cool. But I haven't thought about how to frame that onto a quantum computer. So this is loose, unrealistic airline scheduling problem. And then the homework problem 2 was to reduce this constrained problem to an unconstrained form, and you might have to invent new notation. So that's what you were doing. You were showing me some new notation, which is great because you'll definitely need it, and it's more of a mathematical problem. You can write code for it, but I think it depends on the person. You could solve it completely with math notation, and you would probably need to have the flight which must be scheduled. That was the first constraint. So x0 must be 1. And then you probably need to define a subset of flights that conflict with it. And then those, can have the anti-constraint that they must be 0. They cannot be scheduled with a flight that must be 1. So you probably thought about something like that. And so, make up whatever notation you need to support that. And then your goal, the roadmap, is to reduce it to Cubo, the unconstrained problem with no constraints, and which how to solve. Like, we haven't gone through the details. We will go through the details, but just reading the Python documentation for the PyCubo method, you probably believe that there is a solution for Cubo, even classically, called the DIMOD solver. And then there's a way to do it with quantum annealing, which we'll do later. But in order to reduce we need the reduction. So kind of think of it as like you need to design the Lego blocks to turn a constrained problem into the unconstrained version. So I'll pause there, and whatever questions or comments that brings up for you, please feel free to say it now.
Okay, actually, on the topic of the quantum annealing, I actually found this. Well, I was trying to look up some of the topics before our discussion, and I actually found this scientific report, I think, from nature.com, says benchmark of quantum-inspired heuristics. I'm probably saying it wrong, but heuristic solvers for quadratic unconstrained binary optimization. And it was sort of an interesting read. It was mostly about how, I believe, different quantum solvers actually can implement different problems effectively. They use the D-Wave hybrid solar service. They use the Toshiba simulated bifurcation machine. I think I'm saying that wrong. Bifurcation machine. Bifurcation machine.
Doing great. That's how I say those things. So
yeah. So from there was actually some of the problems. Like, for example, they had these mqlib repository instances, and I believe that is some sort of, I think, I'm not really I need to research this a bit more. This has been something I mostly researched a little later on in the time, and I definitely am still I'm having to do extra stuff in the background, but I think this is definitely some of the extra stuff that I found myself interested in. There was also the not all equal 3 SAT, and I believe that is a satisfiability problem, and that it said, and I'm probably reading off the document, but I believe as it says, it's one of the more fundamental NP-hard problems. And from there, through these sort of problems, I think I may be speaking a bit too much, but essentially for these problems, they have these they go over it through these different through the different quantum solvers, the 8, which they denote as for the D, if I go, let me see, yeah, the D-Wave hybrid solver service. It's an interesting read, I think, in general, that may find interesting if you haven't read it already. So um that was that. I think this one I unfortunately did not get a lot of time to read as well, but this is actually kind of interesting. Do you I remember that you read this paper called the 2D nearest neighbor quantum architecture for factoring.
Yes.
And that was with Krista M. Svor, who if I recall, that was the lead quantum researcher at Microsoft.
Yeah, she may still be the director of the Quantum Architecture Center, but she does a lot of great work. We used to be closer friends, but because we were doing grad school at the same time, and she was like a mentor, for my internship at Microsoft Research. Um, but yeah, please, the previous paper link, feel free to drop a link in the learning log. I'd love to read that as well. But yeah, can continue. That paper is more about architecture and mapping things to a realistic topology. And if that's interesting to you, that's definitely there's a line of research like Chris Kang is a current grad student at the University of Chicago, and he works on Hamiltonian simulation architectures, which is simulating quantum physical systems, being able to measure their energy levels. That is useful for quantum chemistry. That's one thing that people think quantum computers would be good at, like a quantum annealing computer would be much better at than a similar classical computer, and would really show its muscle. Like quantum computing would really flex its strength to be able to simulate these like 100 molecule systems as opposed to 2 to the 100 level simulation that a classical computer might have to do.
Okay, and just as a recall, I believe can you just say who the young? Oh, I think I also have the file, but in general, yeah, I think this is it. Oh no, hold on. Okay, there, I think. Okay, so sorry about that. But yeah, anyways, so sorry about getting distracted for a moment. Who was the person you were speaking about, and where are they located? I think University of
Chicago. Yeah.
Okay, University of Chicago. Okay. And
Chris Kang, Kang. So you can Google him. Like before that, he did an internship at PNNL, the Pacific National Laboratory, in Washington State. And so he spoke briefly before he got into grad school, and now I know he's working on his degree and working with Fred Chong. And I haven't talked to him since, but he may have written some survey papers, or I know his research area of interest is called Architectures for Hamiltonian Simulation, or just Hamiltonian Architectures. And that may be something that you're interested in. So.
Okay. All right. So I think I'm just going to quickly send over a link. Or no, never mind. Sorry. So.
That's okay. Drop it in the learning log, because if you put it in the Zoom chat message, it'll disappear when the message is over. I mean, it's recorded, so I'll find it eventually. But in general, the Google Doc is the best place to put things for both of us to keep track of for a long time.
Okay. Alrighty. So I'm going to go ahead and at least find the thing that I was looking at. Okay, there we go. So here I'm going to get this link real quickly. So give me a moment.
Yeah, no rush.
So this is there, I think. Okay, hold on. I think I need to find the actual. All right, I found the file for where I found it. So I'm just going to go ahead. So, okay. All right. So from here, I think I'll go ahead and insert the file. So
if you're able to, yeah, I don't think I've ever been able to insert a PDF directly into a Google Doc, but definitely a link online. If it's like on archive or nature.com, then you can copy and paste the link into the Google Doc, and it'll highlight as a link, and both of us can click through it to access those documents.
Alrighty. So I think this is what I was looking. Yeah, that's it. Alrighty. So I'll go ahead, put the link in the learning log here. So that you can read at your own leisure.
Sure.
So I hope I didn't do it any injustice in my basic explanation of it, but I definitely think that it was an interesting read. To read through and look through some of our own like materials and see how it compares to some of the more recent and more like top of the notch quantum computers of today essentially.
Yeah, for sure. I mean, like the next step is to map this to accurate topology. You know, there are these quantum computers are not completely connected graphs. Qubits are not completely connected graphs. Not all qubits talk to other qubits, and so you know you could go up with an equation to optimize. You know that sigma of all the xi xj's, but that's assuming that all xi's can talk to all xj's, and then when that's no longer the case, you have to do some mapping with some in-between variables. Like you might need to introduce an xk to connect an xi and xj, for example, and that will take up some resources in the computer. So the Python module from D-Wave, I think it might be PyQo or another, will contain a solver like that, and it will give you a mapping. Like you can actually print it out. And the topology is interesting because it's a bunch of qubits are drawn as these either vertical or horizontal loops, and they couple where they intersect. So all the horizontal ones can connect with or couple with the vertical ones, but two horizontal ones cannot connect with each other and two vertical ones cannot. And then there are subgroups like that. So you can think of like multiple clusters connected in that way, and they have different names like Chimera, and I forget the other graph names, but I think the state of the art is like 2000 qubit quantum processor, and then they're working on a 7000 one. And in each one, it's not just the number of qubits that increases, which would be equivalent to like the number of flights that it could maximize and schedule and optimize at the same time. But they also want to improve connectivity so that you are wasting fewer resources on the overhead of coupling, of like the lack of this arbitrary connectivity. So that's the connection to the nearest neighbor architecture. If you're curious, like we can solve this completely in a simulated ideal setting, and then when we map it to a realistic topology, we'll do some things, and we'll see whether we can preserve a quantum advantage.
Okay, all right. So in that case, I think I wanted to go a bit over my problem solver. I think when I went over it, I kind of went over the code itself. Oh, I did not mean to do that.
Well, I'm interested in seeing your code, especially if you ran parts of it, or if you were able to show schedules. Like, did you get as far as like maybe getting a sample schedule out, and did you like count the number of conflicts, or see like, was it a feasible schedule? What did it cover, like a reasonable percentage of the flights available?
All right. So in this case, I feel like at this point I kind of just separated the code out somewhat. So I mostly focused on just focusing on it, on implementing it into Cubo, which I feel like I probably, that I think about it, probably did a bit of a more poor job at. And then from here, kind of going on to the quantum code. So from here, I generally create. I actually originally tried to run this with 100, but the issue is if I set all of these values to 100, I go here. I need to, let's see. So, and then right here. All right, so if I set all these values to 100 and I try and run this code. I think I just press this button right here.
That
And
sounds quite ambitious from the beginning, but I would be amazed to see what comes out for 100.
yeah, it says that it's the maximum allowed dimension expected. I believe what that means is I can only contain up to about 80. So I decided, why not try half? So right here.
Yeah, well, great. It's good. I did ask you to make your computer sweat, or at least, but it looks like there are hard-coded limits of 80 qubits anyway.
Yeah. So from here, if I try and run it with 50, oh wait, I think I missed a 50 somewhere. Oh, I think I missed it for J. Oh yeah. So if I run this code, then for some reason it also has an array memory error, which says it's unable to allocate 50 pi b for an array with such a shape. So
That might be petabytes, pibibytes,
maybe
pebibytes. Yeah.
you know what? I'll at least go ahead and do 10. Maybe it'll not make the program implode. I have not done that yet, so we're in uncharted territories. Oh, okay. Alrighty. So
Well, that
okay,
looks like a schedule.
alrighty. So oh yeah, I forgot to do that. So
Yeah, it looks like a schedule that scheduled, all of them except for flight 1 and 2 and 4. So yeah, that looks pretty feasible.
yeah, so I run it again. Alrighty, so now at this point, it's practically.
Yeah.
Oh yeah, I need to put these in parens. That's the issue. Okay, let's see.
Oh, sometimes you need to convert it explicitly. Like put a str outside of the parens. Yeah, exactly. That's just a conversion.
Okay.
So that's nowhere near making the computer sweat, but I think I didn't realize that they had these like guardrails inside, and that the guardrails were so restrictive. Like they didn't let you do 50 variables. They let you do 10 variables, and to explore that boundary, you want to max out as much it will allow you for the memory limits, but then also you want it to take more than 2 milliseconds, because it's not you can use classical solvers at that point. You don't need to approach quantum capability. And you might want a magic variable, which is like a software engineering term, meaning you define a variable constant at the top of your program to be the number of qubits. You can call it variable count or qubit count or something, and set it to 10, 12, 14, something. And then everywhere else, use that variable instead of hard coding the number 10, because then it'll be easier for you to, sweep if you wanted to, or to change the numbers and really discover the limits of the software in your computer.
Alrighty. So I think let's try and see how much we can max out. So I'm gonna, do you think? No. I think I'll do 25 at the very least, because that's a good half number, I think, in between everything. Real quickly,
Okay.
just to see if that number works. But from then, with that exception, I was thinking of the code. Moving on. Oh wait, did I? Oh, I forgot to save. Okay, if I just run this code. Alright, it's taking a couple of seconds. That's
good. It's still chugging. If you loaded your task manager or activity monitor, you could see, if processes are consuming, they're pegging your CPU at 99%, or your memory limit at however many gigabytes it is.
So I'm gonna go ahead and do that. Let's see. Code. Okay, Visual Studio Code, that appears to be taking up a considerable chunk of memory. For me, I'm reading about like 1400 megabytes of memory, and it's running the CPU currently at like 15.2%. I think it's somewhat fluctuating. So
That's that's decent. So 1.4 gigabytes of memory out of, you probably have, 4 to 8 to 16 or 32. And but it's nowhere near like redlining or getting killed. If it runs out of memory allotted to the process, the operating system will kill it. And I feel like we're not near that electrified fence yet.
yeah. Okay. Alrighty. So that alrighty. Okay. I didn't know that include. I mean, it is super polynomial. I mean, this task I believe is super polynomial, and I think Kibo does lie within the range of an NP hard problem. Like I think. Oh, hey, it did it! It did
Oh,
it!
only
Yeah.
99 seconds. Okay,
Uh,
yeah, that's
hey.
not that's not the lifetime of one scientist. So it's so we have some data to take from this. Okay, and it gives you a schedule, which even just perusing it. I mean, I guess you can copy and paste that into an interactive Python session and count the number of ones that it's scheduled, but it looks like a majority, but less than before. So it was harder for it to find a feasible schedule, and M in this case, might be 10, as opposed to 3 like last time.
Hmm.
So that's an interesting thing to note down. And there are heuristic solvers that are completely classical that are not like trying to simulate a quantum computer. And my suspicion is that they run much faster. Like that you could go with them up to 100 variables if you wanted to. So that follows along with, you find your own research links, which I actually think is a great practice. So if you ever find a direction you want to go explore, we can focus our lessons on that instead. And so one direction that you could explore is to find the best classical solvers for Cubo and see how well it compares to this one, to PyCubo. In addition to finding a limit, right? Like 25, was not the max, and 50 is too much, and you can, maybe set it overnight with a script and have like a whole high-level function that runs your test, and then like times how long the solver takes, saves the schedule it finds, counts the M, counts the number of conflicts. Oh, wait, that's not correct. It finds it wouldn't be the conflicts. It would be the number of flights that it couldn't schedule. So that, we might need to make up another term for that called like coverage, for example, right? Like you desire coverage to be 100%, and it may only be 70%. Like this schedule looks like it has a coverage of about 60 or 70%.
Okay. All right, so that's something interesting. So in that case, I think for this part, maybe maybe I should maybe at this point, maybe we could work on trying to implement some of the best classical solvers and compare it to PyCubo at least.
Yeah, I think that would be good. Some of them may be available online. Some of them may be software on GitHub. Actually, it's probably like where you might search, especially if it's a research paper on arXiv. People do it a lot where they publish, the scientific preprint on arXiv as a PDF, but then they link to the GitHub where you can try their source code out. Yeah, that's like a very common practice for scientific papers now, especially for AI.
Okay, so let me do this real quickly. I'm going to pause sharing my screen here.
Sure.
And I'm going to go ahead and share my screen right here. So I think, okay, there we go. That's what I'm looking for. So I don't think I need this anymore. I may just I'll probably keep it on for a little bit. But for now, I'll go ahead and at least try to see about this. Oh, I see this, so maybe
Oh, looks like there's a lot. Yeah, we found something called cubovert last time, but cubo chimera, that sounds like it's the exact D wave topology, the architecture called chimera.
okay. So I think I'm thinking that's probably I don't know if that's exactly quantum, but I'm thinking based on the look of it, it's probably because this is done at least about like this is published at least like 7 years ago. I think there's probably more specific timeline for this, but at the very least, this thing is relatively old, and I think it's definitely. Let me try and see if I can have this file. Alrighty, I'm going to go ahead and at least do this on the other device that I'm using. So because that's the one with the code. So let me do this. I'll probably look up this same thing. Alrighty. There we go. That's the thing I'm looking for. Okay. So I'll probably add file. Oh.
What's wrong?
All right. So I think let me see if I can just do it here. If I go to upload files. So maybe oh no, I'm using the wrong thing. Oh. One of the important things about being a computer scientist is to actually read stuff before you press it,
Sometimes.
If you look at add file and think, hey, that's the part where I'm going to add a file to my computer, it doesn't work that way. And unfortunately does not work out that way. Okay.
Well, yeah, you don't have permission for Alex Selby's repo, but you can fork it and then you would. So, but
Okay.
you also are probably more interested in cloning his repo locally, possibly forking and then cloning your fork of it. And then you can add and test. You can actually run it with these Python commands. We went through all that work to get Python to work on your command line last time. And so now you can use that. You can download, you can clone these Python repos and then run it on your computer and see it, stress out your CPU and see what results they get. Yeah.
All right. Yeah. I'll let me see. Let me go ahead and probably just go ahead and copy all of this down. So I think files that may be most necessary. Okay. You can see some of them, but all right.
Yeah, we may not have installed Git on your computer from last time, but if not, we can. There's graphical interfaces for Git on Windows, and then there's command line Git also that we can use.
Okay. All right. So I'm currently forking the file now. So, alrighty. So now I just need to pretty much save all of this. So, ooh, interesting. So I'm seeing some of the things that he's adding. So when I forked it, there's also this added n8, n equals 8, and n equals 16 for harder instances. So I don't know if that's a predictor, but maybe. All right. So from here, I think.
Yeah, I mean that was 10 years ago, and it could be that the Python simulation was so inefficient that they could only do 8 variables, like 8 flights to schedule or 16 flights to schedule. But you could probably do, much better with modern PyCubo.
Yeah, absolutely. So let's see. Let me see if I can go ahead and download all these files. Give me a moment. So sorry.
Oh, no worries. This is what the time is for. It's all scientific inquiry.
Oh, is that it? I feel like that was it. Okay. So now I'm currently downloading this file. Hopefully it doesn't have any malware. All right. So I'll probably go ahead and share this screen that where I'm currently downloading everything on. So here, give me a moment. Okay. And, no, that's not it. Okay. I think, yeah. Okay, there we go. So, okay. So from here, I think it's just currently downloading. I've got this tab right here. So it's about a good chunk of megabytes, I believe.
Yeah, I also saw in the code button in the drop down, one option was GitHub Desktop, which is one of those graphical interfaces I mentioned. So if you wanted an easy way to git clone, to download the code in a way that you can commit and upload changes, with version control, GitHub Desktop looks like something that's designed to work well with Windows.
Okay. Okay. So I think from here, let's see. I don't know how long. I don't know how long this is gonna take. So
Okay, I'm surprised there's that much there for the code, but maybe it's pretty involved. Like maybe they save, because Python source files by themselves are just a few kilobytes, so there must be something else going on here.
yeah, maybe. So I do want to kind of suggest an idea that I've been thinking of recently. So, oh, sorry. So I've been reading this book. I think it's by Nielsen and Chang. It's basically on, I don't know where. Give me a moment. I need to find it.
Yeah, it's like the seminal textbook, Quantum Computing and Quantum Information.
Yep.
By
Okay.
Neil Strong. Yeah.
Yeah. So I've read it, and I remember from that class that I was taking about the no cloning theorem. They kind of just said it's kind of true, but it's actually kind of interesting in how it's presented. I think you probably know how it's presented. That it's the CNOT gate that is presented, that generally the CNOT gate for cloning, the classical equivalent essentially clones like a target bit, right? And
Well, an entangled copy, so it's but you're right. They go through and show that it's impossible to make a separable copy of a cloned qubit.
okay. So just as a general question, I feel like this is bordering a bit more into the land of like in kind of practical what if, but is there some sort of quantum equivalent? I feel like this may be a little more of a stretch than anything, but would there be potential for there to be a quantum circuit that may be different from a classical circuit but still sort of applies the cloning instance in a sense?
I mean, there are other kinds of cloning, and then you can approximate, but to approximate a separable cloned state, I think can be shown to be like expensive, like as expensive as preparing the state from scratch. So, if you knew classically that you wanted to prepare the state, like 25% ket 0 and 75% ket 1, and you wanted to prepare it once and then clone it into separable copies, probably you would discover the circuit to do that would be to approximate it even to like, arbitrary precision of 24.9% and 75.1%. But that to do that would be almost as expensive as just reproducing your classical circuit or sorry, reproducing the circuit that produced the original state to begin with. So I don't know an actual result to show that, but I know, yeah, in Nielsen and Chuang, whatever they present as the no cloning theorem is to show it's impossible. And then there might, if you search on archive.org, there may be results where someone shows how close you could actually get to cloning, and to show that it's really expensive to do.
Okay, that's definitely interesting. So,
And also has, sorry to interrupt, but this is some people have at the beginning were using this as sort of like the no DRM. Like if you were an evil, recording company and you wanted some data that you definitely did not want to be copied, quantum computing, in that sense could provide it for you, but also maybe be more fragile than you liked. Like not only could you not clone like this piece of music that you've encoded into quantum information, but that if you didn't keep error correcting it sufficiently, you would, lose it forever as well, or it would degrade.
Yeah. I think I remember that process. Like, I think there is a more specific area for that. I know like there's like different like sort of like encryption techniques. One is like public key transcription and private key transcription. I know that private key transcription is generally the idea that like Alice and Bob have like two private keys in a sense. The only difficulty in that, like, if an eavesdropper tries to break in, they can't like decode the information if they don't have a private key. But I know that generally it's impossible to try and distribute out the private keys themselves because, if you try and distribute out the private keys, how do you know that an eavesdropper doesn't just grab the private key, pretend to be Bob, So sort of the interesting thing with what you said was that like quantum, sort of this quantum computation that like generally a disturbation, like if an eavesdropper tries to get in on data, that it would naturally just sort of disturb it. It's interesting in that sense that it actually makes private keys possible, so at the same time, while there are like, I think quantum algorithms like Shor's algorithm that essentially can create this sort like, or the best way to say is like there are algorithms such as Shor's algorithm that essentially can break most modern encryption. There's this quantum encryption that appears to be almost unbreakable in a sense, and that if you have some sort of perfect, like really usable quantum computer, you can kind of use private key encryption, and like, or maybe even better, you just don't need to use private key encryption. You can just give data freely, and no matter what, like the enemy cannot there's no one who can eavesdrop without their presence being known in a sense. So sniping is almost impossible in a sense.
Yeah. I mean, I like the conceptual discussion. If you wanted to, I can work on preparing some problems in these areas, like about detectable eavesdropping and no cloning for the future, just because I find, even though the discussion is fun, if it's too general or abstract, then it's kind of lacks a bit of rigor as well. And but I mean, that's a good textbook, and the textbook probably definitely does contain a result or homework problems about no cloning. You could probably find something about eavesdropping in there too.
Yeah. So, okay. I know while I'm waiting for this, for the file to fully download, which, oh my gosh, it may take a while for this to happen. I do want to try and spend this time also talking to you a bit more about like quantum computation in general, more so other areas or concepts of it. So,
sure.
I know recently you've been talking about QUBO problems. I think there were also some sort of, I know that in general, like NP problems, like quantum computers can generally are found to not be able to solve those problems. Like the traveling salesman problem is a problem in which quantum computation is just as effective as classical computation, and that it'll only be, quantum computation can only solve the problem in an exponential way. So
yeah, I guess what it sounds like you're interested in maybe is like this boundary of like classically hard problems like NP hard problems on a quantum computer. And I think as you said, quantum computers do not sort of collapse the polynomial time hierarchy. Like they don't if they exist, it doesn't mean that NP equals P, but it does solve some bounded probability problems. There's a class called like BQP. And so there are some NP hard problems that it can solve with high probability. And NP, when something is hard, it means like in the worst case, like if there's any instance which is unsolvable, then the whole class of problems is considered NP hard. But it turns out if you're relaxing that, if you're okay with solving 99% of the problems with like a scheduling, for example, then quantum computers like in real life can do pretty well. But then as we discovered, classical solvers for QUBO can also do pretty well. Like classical solvers can probably also do 100 flights or 100 variables.
So I think an additional thing I do want to mention is that I think in the meantime I've also been trying to look at the David Bacon from University of Washington. I think I've been looking through a bit of his lecture notes and homework, and
Yeah.
I've actually went through one of his problems and solved like just a bit of it. I know it's not really anything too much of discussion, but I think that's definitely an area that we can do.
Yeah,
in addition,
sorry to interrupt. I was going to recommend his course notes as well. The CSE 599D from 2011, maybe, I think.
Yeah. So I think the first problem, I think it's actually kind of interesting. The first problems I think more so are combinatorial problems, and I definitely. And it's definitely kind of interesting to look at quantum computing at these different lenses because it gives you a bit more understanding about it. I know I think that's the current class for quantum computing, at least at University of Washington. But
there is no current class that I know. That class has been taught for a long time. Aram Harrow taught a follow-up class, which is more quantum information based. But if you find those course notes and go through them, I think they're the latest that are taught there. And I think Aram teaches more recent classes at MIT, but I haven't looked at them recently. So if you wanted sort of classes that covered more recent results, but I think it's good to start with the basic results. That's a graduate level class. And I think the problems you're mentioning are for like rho major and rho minor matrices, which kind of they kind of get at like, why are quantum computers different than a, probabilistic probabilistic quantum computing. And so I think Dave frames it in a pretty interesting way. So we can, work on those next time in addition to QUBO or instead of QUBO.
Okay. So I think I remembered where the class is. The lecture notes I think are from the 2006 class for CSE 599D, more specifically. And so I think we're almost out of time, but just one last question I kind of want to ask. Maybe if this doesn't take too long. I think you said you were going to be teaching.
I am teaching, not anything quantum. I might touch on quantum briefly, just because from our conversations, it made me realize how much I miss it. But it would probably be like quantum annealing and maybe some discussion of double slit or maybe something about analog computers as well. But yeah, it would be at the Evergreen State College this fall, data structures and algorithms, and I might spend like half of 1 week talking about quantum algorithms. Okay. But it wouldn't be at the level that you've covered over the summer. You're already way past the level that I would be covering it at.
Okay. All right. So I think I have 1 more minute. I'm so sorry. I may just
that's okay. We started late, so we can run over. That's fine.
Yeah, I think I just have like 4 more questions I'm probably going to ask you, and then I may just end for perspective time, and this file is taking long to load. But I think in general, have you been able to go to Georgia Tech?
Have I been able to what?
Have you been able to go to Georgia Tech? I know I haven't been able to visit, so I just kind of want to know like how it the colleges in general.
Yeah, well, I'm at Georgia Tech right now. I'm in my niece's dorm room. She's like raising the roof over here in the corner, and um, yeah, we haven't been able to go in any of the laboratories or talk to any faculty. I used to know Ken Brown, who's a professor in chemistry here, who actually I think is doing a lot of quantum chemistry simulations, as close to quantum computing as you can do in the chemistry department. I haven't talked to him in a long time, but he was faculty here. But this is like, school isn't starting for another week. That doesn't matter for grad students. They're probably still, in a laboratory or in a library somewhere. So I don't know a lot about the program here. If you were interested in it, I would keep reading, whatever. I can give you the name, Kenneth Brown. You can see what is on his group's website and read their paper. They're probably more experimental and, for chemistry majors or quantum physics majors. Are you a junior or a senior, if you don't mind me asking?
I'm going to be a senior this year. Yeah. So.
Okay.
Senior.
Wow. So still very early to be thinking about it, but yeah, you can look at what research is on Ken Brown's website to see if you're interested in coming to Georgia Tech for that. But, honestly, I would say like for undergrad, there are a lot of great programs everywhere, and you can just, apply to a bunch of them. And no matter where you get in, if you are interested in grad research, the undergrad program doesn't matter. There are a lot of great schools. And then when you're in an undergrad program, then you can try to do research in the area. And then I would say once you're in a college, then you can sort of approach professors or faculty members doing the research you're interested in, and then be able to offer them something. I may even be able to find like the first cold email I wrote to Isaac Chuang saying like, I can build electronics for you. Like, please let me into your lab, or, if there's anything you need done for quantum computing. And that sort of started my journey. But I would always recommend getting into the college first, which could involve research, but often just involves getting good SAT scores and writing good essays. And well, I'm not really sure. My niece has much better advice than I do, so I can put you in touch if you're interested about how to get into college. But once you're in, then you can try and approach a professor and then take their classes and be part of their lab. They often hire undergraduate research assistants. That's a thing to look out for colleges also. It's like whether they let undergrads do research. Not all colleges do. Hopefully Georgia Tech does. I know my niece would be interested in doing astrophysics research. Yes, these are all good things to look for when you apply for college. See if they also offer grad degrees, if they have faculty research that you're interested in, and that they let undergrads do research, so that you're already thinking about how to enter that world. And if you're really interested in it, then it'll be inevitable. You'll enter the field, and you can be a grad student. It's really rare to find like really motivated, curious students. So I think if you continue in this direction, you won't have any trouble doing the research that you want to do.
Alrighty, thank you so much. I think I just wanted to point out a couple of extra things. I know this, but no, I don't think it's really just really mostly remarks on my part, So
Sure.
I don't think they're really important, but I may just mention this. I know at least this person on TikTok who goes by Blue Hand Coding. I think he's starting at Georgia Tech this year, and I know he does projects with Arduinos and makes videos. So I know at least that's a person of interest. So I know at least in terms of college goals, I'm kind of hoping to go to MIT, Caltech, or University of Washington. But I definitely think that Georgia Tech, from what you've said, is definitely on my radar of colleges that I may want to apply to. So,
yeah, I mean, reach out to respond to TikTok posts. That's actually a good way to make friends. Also, my niece is listening. I've never recommended her to go into TikTok before, but maybe for research purposes, it's okay. Not just Taylor Swift dances or whatever. And okay. And I don't know if anyone any faculty doing research at University of Washington, but I can give you a short list. You know, there, Robert Rasendorf used to be at University of British Columbia, which is like north of Seattle of UW, and that's close to D-Wave anyway. So that's like a great way to collaborate with that department. And then Waterloo, which is like the MIT of Canada, they have the Perimeter Institute, so they have a huge department devoted to quantum computing, and that should be on your list. And then if you're willing to go to think about Europe, you know, Innsbruck University in Austria is a big experimental group, and they're close to the Max Planck Institute in outside of Munich, which has like sort of they do experiment and theory. And then there's Keio University, Keio in Japan, where Rodney Van Meter is doing more architecture research, like the stuff that you were reading in that paper that I did with Krista. And yeah, but in addition to thinking about colleges that have the faculty researchers that you want, think about colleges that are close to companies that offer internships. You know, like Microsoft Research has great internships in quantum computing, and they're in the Pacific Northwest. And D-Wave is also up there. And then there are a lot of quantum computing companies. There are more than there used to be. There's Rigetti, which spun off from IBM. IBM also has quantum hardware, which is like, you know, the summer session you did with Qiskit that comes out of IBM's research. And then there's a company that does the linear optical qubits called Xanadu, like from this poem Xanadu. I don't know if they're still in business, but they're like the only people doing linear optical qubits, which is a cool approach. And then Google, yes, they call it quantum AI because it sounds sexier that way for sure. They're getting a lot of press, but they do both. And I think Dave Bacon, who's no longer at UW, he still is in the Seattle area. He's still a Google engineer, and I think he made his way back to quantum. For a while he worked on a bunch of other stuff, like non-quantum stuff like Google Domains, but now I think he's back in working in their field. And so even if there's no one at UW doing faculty research, like if you're in the Seattle area, if you have a reason to be in UW, you can actually go talk to Dave. He's a wonderful human being, in addition to being super smart. He'd love to have coffee at Google in the Fremont offices. I think that's where he was. And Krista, I think, might still be in Seattle too, because she's raising a family there. And yeah, so Seattle, for a number of reasons, is also a good place to be. Seattle, Boston, Waterloo, and then, you know, Germany, Austria, if you're interested in that part of the world. So
okay, oh my gosh, these are all great. I mean, when I heard of quantum, I think this was definitely one of the things that excited me the most, just generally because it's something that's like so fascinating yet like so new. Like it's sort of a very new topic of field that like you can kind of get your hands into and like start like actually like getting your hands on to like direct research and like start to really sort of make a change in the world. So that definitely made me sort of excited. So I think I know it's definitely hard to tell who's doing research. I try to research it on my own, and it's definitely, the names have definitely helped. I think there's also I know there's Stanford that's actually having a lot of money on quantum research, but I think my teacher from the previous class, I think you may know her. Her name is Laura Lewis, I think. But
I've been out of the community, but it's a really friendly community. So I would say that yeah, it's easy. People are really willing to help you to get into it if you want it. So.
Okay. This information is so helpful. Thank you for trying to help get me into this community. I'm really excited to try and be like a part of this whole research and try and make a difference in the world. And thank you for trying to like help me become a member of it, essentially. So
sure, my pleasure. So I will, keep working on the the homework problems like as we described them, or take the tangents that you want to, when these files get downloaded. And then, as long you can keep coming up with your own questions too, which I think is the first step to getting involved in research, is sort of developing what your interests are and your own tasting questions. So yeah, let's stay in touch, and I'll see you next Sunday.
All righty. Thank you so much. Have a great rest of your day.
You too, Caleb. Bye.
Bye.